Good morning, class. So today we will be continuing with our combination logic circuit topic. As you know that we have already discussed about basic logic gates, their truth table, and basic logic functions, different types of ICs, and their electronic characteristic. So today we will discuss about how to make logic expressions or the mathematical expressions for different logic functions. How to do that? It's pretty simple. Basically, the basic logic gates which you are looking at on your screen, they perform basic arithmetic functions like addition, multiplication. So these functions are very useful for us in order to develop a digital circuit which can do from basic to complex numerical questions for us, like in you see in your calculators or on your computers, from the basic function of addition, subtraction, multiplication, all over to complex algebraic equations, matrices, and complex equations. So first of all, I will tell you how to write the functions uh, for different logic gates, as you can see on your screen. The first one on the left is the AND gate, and this is the function. That's how you write it. F stands for function. So if you write f a comma b equal a dot b, so this is a complete way to write the expression. This thing here on the left, it defines the function, that this function f, it has how many inputs or how many uh, digital signals available. So here you can see it has two, A and B. It is referred here in the bracket. So here you can see A and B written in the bracket. These are the two functions. Sorry, these are the two inputs which this function will be dealing with. And because this function is for AND gate, so you will see a dot sign in between. Dot is for multiplication. So this function is basically doing multiplication of the two inputs, which are A and B. So that's how you write the expression. The same procedure you will follow for OR gate. For the OR gate, you will write it in the way. First of all, you will write the same function with two inputs A and B, comma in between, and then simply you will write A plus B. So this will become the function of OR gate. And OR gate, as you know, is doing multiplication, which you can see here. The third one is a basic one. It is the NOT gate, and as you know, in the NOT gate, it only reverses or inverts the input signal. So there are different methods to show that. So you can see on your screen f. Now this time this function has only one input, which is written in the bracket as a. So here you will write the output as a bar, or you can write as a with a slant symbol like this. So any any way you like, you can do, you can adopt any one of the method. So it's basically inverter is a very basic gate. It only inverses the input signal. If it is 0 is coming at input, it will make it 1 and vice versa. So based on these basic expressions, now we will look at more complex expressions. So let me move on to the topic where we were. I hope these expressions are easy for you guys. Is there any question on that? Okay, good. So if I write a combination of logic, for example, I will start with the easy one. If I write f and I write two functions here, a and b equal. Now this function, what should it do? We should express it in the form of a uh, arithmetic expression. That expression, there are two inputs. For example, if I say I want output as a bar dot b, so I have written a very basic logic function. So what do you think, how, I mean, to perform this logic function, what type of gates combination we should use? If the bar is not there, as you can see, there is a bar here. If this bar was not there, this one, then it would have been a simple AND gate doing multiplication of two signals A and B. But here is the problem. It says A inverse, or so it means we have to first invert input A and then multiply with B. So how we can do that? We will look at it in a minute. So it means we don't only need an AND gate, but we also need a NOT gate. So we can make a NOT gate, okay? And there are two inputs, A and B. Because we need to inverse the input A, so we are putting NOT gate. We are connecting NOT gate to input A. Now after this, the output will be now A inverse. So it will be now opposite. Now after this, we can use a NAND gate, which will simply multiply these two functions, and we will get A inverse dot B. So this will be our output. So that's how, if in exam, if I give you a function like this, which you can see on top, and I ask you to develop a logic circuit for that, so that's how you do it. You just have to look at that what this function is doing. So you can easily see that it is doing actually multiplication. So you will need a AND gate. But you have to be careful. You have to look at the inverse symbol here. So it means you need to have one more gate, which is NOT gate, to make the input A inverse. So which you can see here. So simply in the path of A input, just put the NOT gate. It will inverse A as A bar, and then you can put it into a AND gate for multiplication function. So this is a easy example. Now if I go for another example, a little more complex example, let me think of three inputs. So now there is a function which is dealing with three inputs, A, B, and C. So now this here I'm not using any inverse thing. See, there are three inputs A, B, and C, and how what we want out of it, we want to add input B and C together. That's why they are in a bracket. First, we have to add B and C, and whatever is the result, we want to multiply it with A. So I hope it's an easy one. So what I can do, I can first of all I can bring three inputs A, B, and C. Which of the two inputs I need to add? Those are B and C. So what I will do, I will just simply put a OR gate, because OR gate is used for addition. So I will put a OR gate. The output of the OR gate will become B plus C. Now this I need to multiply with A. So I will just bring it here. For multiplication we use AND gate. So we can get it A dot B plus C. So I hope it is easy. You just need to remember that for multiplication function you have to use AND gate. For addition you have to use OR gate. For inversion you have to use NOT gate. So this is how this whole logic circuit will develop, just by looking at the expression, this expression on top, and based on that you can develop uh, the combination logic circuit. So this is the combination logic circuit, because you are actually using more than one gate. You are using two, three, or more than that, and you are dealing with different inputs here. Now if I do a slight change in this, for example, I will mark it in red so that you can see it clearly. For example, if I put a bar on top of A, you can see a bar. So now what I have to do, there is a bar on top of A, so it means I need to multiply A inverse into addition of B and C. So here this thing is wrong now, so it should be A inverse. What should I do? Simple, I should put a NOT gate before this AND gate. So I will use an eraser here. Let me just, who is drawing this? So what I will do, I will use red color for that so that you understand. So now as you can see, let me erase this as well. Okay. Now, so guys, this is the change which I made in the expression. You can see the same change in the logic circuit here. So instead of A, if I have to use A inverse, I just put a NOT gate. Okay, now A inverse is coming to the AND gate, and it is multiplying B plus C dot A. So here also the change will reflect. Now it will become A inverse dot B plus C. So guys, any question on this? All right, so good. So I hope this is interesting and easy stuff. So you can easily think of different logics. You can develop different logic functions, and based on that, you can create logic circuit like this. And you can do the reverse as well. For example, if I give you this logic circuit and I don't give you the expression, then you can create this expression by just looking at the logic circuit. So that's how these things work. Now there is one more thing, truth table. You remember truth table? We have a specific truth table for each gate, which shows the behavior of that gate, that which logic that gate is following, following a multiplication logic or addition logic or inversion logic. So you have seen logic truth tables for different logic gates. So you can also develop a truth table for this combination logic circuit. Okay, this is not one logic gate. There are three logic gates in this circuit as of now. So you can also create a combination of these logic gates. You can create a truth table. That I think I will show you in other examples because there is not much space here. So, or let me try something here. Okay, so in the logic, when you are making a truth table, you need to mention your inputs first. We have three inputs here, A, B, and C. Okay, then this is your output. This is the function F, this is F output. So this is your output. So after three inputs, you can mention the output column. But this truth table is not straightforward. So it is better to make additional columns for each one of this. For example, uh, addition after B and C, you can make one column for that. Inversion, A inverse, you can make one column for that. Then do this A inverse dot B plus C. So you can break it down. You can make one column for each stage. It will make your job easy. So for example, here I will put A inverse. Here I will put B plus C, and here the final output, which is A bar dot B plus C. This is the final one. So that's how you can make a truth table. So this will help you if you are putting all the stages here. For example, this one, these are the additional stages. If you put this here, it will help you in order to develop the truth table. Now the inputs, you know, if you have three inputs, how many possible input functions you should have? One, two, three, four, how many? Remember I told you a formula. The formula is 2 to the power n. No, Rashid, it will not be 4 because we are dealing with three inputs now. So if you 2 to the power 3, it will be 2 times 2 times 2. So the answer will be 8. So you will have 8 different input combinations here. So this will help you so that you don't miss anything in the exam. If you are asked to make a truth table, you can use this simple formula to find out how many input combinations would be there. Okay, so the input combinations, the first one will be obviously 0 0 0, then 0 0 1. So sequentially you will keep on changing the states. So the C, which is the rightmost input in this column, so we will make it 1 this time. Now in next step we can make B as 1 and C as 0. In next step we can make A as 1 and other two 0. So that's how you will continue making it. I will show you a few complete truth tables. From there you will have a good idea. So there is less space here, but you can see truth table in other slides, which I will show you in a minute. So that's how you can do three things now. Now I will sum up the whole lecture. We talked about the expression, which is here. We talked about the logic circuit, which is here. And then we talked about the truth table, which is here. So all three are connected. So from the expression, you can create a logic circuit, or from the logic circuit, you can create the expression. And if you have any of these two things available, either the expression or the logic circuit, you can develop a truth table. For the truth table, no need to have a logic circuit. Even if you have a simple expression like written on the top, from there as well you can make a truth table. Truth table will just give you the complete behavior, the complete working of the gate, that how the gate will be performing, what outputs it will give for various different input combinations. So truth table is kind of a summary that how it will behave. So I will stop the recording here. The topic is almost complete.